I'm going to get the lenses black, and you have to do your own laser etch or whatever you want on the lens cap. And ultimately, this device you'll be able to put on your CAN bus and send it and receive CAN messages from it that occur every time you press a button. A CAN message is sent, and if you can detect that, you'll know the button's been pressed, and you can send a message back to say light up the LED ring around it as either amber, red, or green, or any of the two flashes where you press a button, it sends a CAN message, you get it, send back a CAN message, and then it'll unlight the ring saying that it's on. And I have no idea what you're going to use all that for, but it has to be useful to somebody.
Yeah.
Let's talk a little bit about Arduino and CAN. We set out to do a generalized electric vehicle control unit, so I could sell 90 hazard-dynamic DMOC 645s and associated Siemens motors. I later acquired another 100 Siemens motors. I'm not too sure what we're going to do with those. And we elected to use the Arduino DUI as the hardware to affect that control. And we did so for a couple of reasons. One, there's 4 million Arduino DUI users. The IDE is very simple and free, and there's a lot of code support, libraries, and shields. Shields are things that plug into the Arduino and give it added capability that were already out there. There are better microcontrollers that I like better, that Colin liked better, but they didn't have those traits. And so we went with the Arduino, and they had just released a thing called the DUI, which had the Atmel SAM3X 32-bit microcontroller, 84 megahertz, about 500K of memory in it, and so forth. The history of Arduino: Massimo Banzi and maybe 3 or 4 of his friends taught school in Italy and met at a wine cafe that was named after an 11th century Italian king named Arduino. And they were trying to devise a device that would aid them in teaching students how computers worked, and their focus was in the real world, not for text processing and numeric processing, but how to turn lights on and off, and switches, read switches, and buzzers, and motors, and so forth. And they developed the original Arduino, a somewhat smaller board than this, that was basically an Atmel 8-bit multi-controller, microprocessor, with all the pins brought out to plugs on the edge. Now, understand they're not protected or anything, they're just brought out to a socket where you can get to them, because these chips are so small. A real one of these things, I can't even see these individual pins, but here I can. But their main innovation was to put a bootloader on the USB serial port and connect that through a chip to the multi-controller. And that let you write a program and upload it to it, and it would load it into its memory and then execute that program. The original thing they chose as an environment was a language called processing, and a program was called the Sketch. And they originally developed this to kind of be an anti-programming program. where they could teach art students and so forth to program, and it would be easy. Fortunately, they were kind of geeks, and they screwed up. And what they had selected, to my delight, is basically C++ underneath. But they added some commands that made it easy to access pins. And they numbered the pins, and you could say set this pin high, or set this pin low, or read this pin, or write to this pin, and so make it real how to control external devices. There were some that have an analog input, and they could read a 0 to 5 volt signal, and it would assign a value, a decimal value, digital value, between 0 and 1024, depending on whether it was at 5 volts, the 1024 end, or 0 volts, the 0 end. And so it would assign a numeric value to an analog input. And so you could control things. But I think the innovation was the USB bootloader and the use of this basically free IDE. It really used the already existing GNU compilers. And so in theory, it would work with any language, but as presented, it's very close to C++ without the massive STL library, which admittedly is a big part of C++, and you don't have that. And so we can write little object-oriented C++ programs and upload it to this microcontroller and make it do our bidding. And again, why we went with Arduino was because of the familiarity with this software, with the many people writing the software for it, and with the hardware that was out there that would work with it. A not very tragic miscalculation on my part. This was introduced the month we started the JetCube program. And I assumed the Arduino community would be taken by storm by this much faster, much more capable 32-bit multi-controller. In the interim 2 years, they have grown to virtually ignore it because of a couple of near fatal flaws. The first one is that this chip uses a 3.3 volt logic. If you put 5 volts on one of the input pins, it destroys it forever, and you're allowed to buy a second one. The second thing was this particular chip had no EEPROM in it, and the earlier Atmel 8-bit chips would have a little bit of EEPROM, like 1K or something. But you need, EEPROM is electrically erasable, programmable read-only memory. You can write to it, take the power off, put the power back on, go read it, and it'll still be there. It doesn't need power to record data. And almost everything I've ever done with an Arduino had some configuration items that I don't want to put in every time I boot up the program. So you write those to EEPROM, and they're persistent, or what I call persistent variables. It doesn't depend on the power state. They're always going to read that. They're like constants. And so it had no EEPROM. And as a result, most of the shields didn't work with it. And a lot of the libraries didn't work with it. And a lot of the code didn't work with it. And so it's almost been a little bit of an orphan in the Arduino community. But I didn't know that when they first rolled it out. And I've grown to like it more and more ever since we've had it. It did have a CAN controller, but actually 2 of them, built into the chip. But recall I said that the hardware for CAN comes in 2 pieces, a controller and a transceiver. And they did not put the transceiver on the Arduino DUI board. So CAN is in there, but it's totally useless. They have no EEPROM, etc. This is actually We call this the EVTV DUI. It's kind of a joke. Arduino takes exception to people building things and calling them Arduino, and I don't blame them. And so we don't call ours Arduino. But it's a DUI compatible with a couple of key changes. Here is a 256K EEPROM, quite a large one. EEPROM chips are desperately cheap. I don't think that's $2. And here is a CAN transceiver, and it's hooked up to the CAN controller in the chip. So I've already got CAN. I can do CAN. And I never liked the 12-volt barrel connector in a car because it's not very strong and it comes loose. And so I replaced that with 2 screw terminals that I can mash down on and squeeze the wires until they won't let go and they won't vibrate loose, in theory. And ran my CAN high and low out there. Again, thinking I needed to terminate each time, or not, I put these little solder tabs that you have to put a solder bridge across to connect this to a couple of resistors and a cap to terminate it. And it turns out you always have to do that. It's just, I've been burned a number of times now. I just solder those. And in fact, on our shield, we made it a switch, not a solder lamp. So this is an Arduino DUI that forfeited one USB port. The DUI had 2 ports, and in favor of a CAN transceiver and an EEPROM chip. And that's most of the change. I told you about the integrated program. This is the IDE. At any time and from time to time, you can go to Arduino and download this and install it on your laptop. That's a Windows laptop or a Linux laptop or a Mac laptop. They have versions for all 3, and this is what you get. And this is a program that I've written that doesn't do anything. It's called the CAN skeleton. And what it is, some things that I do in every program, and I don't want to keep typing it in. It's kind of like the persistent variables. So I just have a outline program that has some things that I already do. All Arduino programs start with a series of includes, and these are libraries, and they're simply other programs. And they are sucked in and compiled with the program you're writing. And the effect that they have is to extend the language. So let's say I have all the generic C++ commands that you would get out of any C++ book from Amazon.com. And I have some Arduino commands that are specific to Arduino about pins, mostly about pins, reading pins, writing pins, setting pins high, setting pins low. Those are extensions. They're not part of the C++ language. They give you additional capabilities for the Arduino hardware. But we've just added some hardware, CAN transceiver. And so I want to include a library called DUICAN.h. And I just put an include here, and that tells the compiler to compile that program at the same time it compiles mine, where I can issue calls to it and it'll be in memory. DUICAN was created by Colin Kidder. Colin and I met during the Machina, a company called Recharge Car, I think, had done a Arduino Mega board with CAN on it. They used a different transceiver, but it didn't work very well. And it did a couple basic things. I said, hey, here's the spec sheet for this MCP 2551 or something, 2515. it does all this masking and filtering. Why can't we do any of that? And Colin said, well, we could if we just wrote the software. I said, well, this we thing, were you thinking maybe you or you and me together? And he's kind of a quick coder. He said, well, actually, while I was thinking about it, I did it, and here it is. And that was the first version. And he's worked on it some since then. And so when we went to the Dewey, he ported that MCP 2515. We actually use a completely different transceiver chip, and it works quite differently and so forth. But he stayed with that, and but that's where Colin and I originally met, was over the recharge car Makina Arduino Mega Board. And he's the author of Dewey Can. And this gives us some CAN commands that make writing software for CAN so easy you're not going to believe it. And whenever, the few times that I'm on another kind of Arduino board and I don't have my Dewey Can, I'm reminded why Colin's cool. Because they do it really, really badly. And he's a very gracious person, so he tells all of them that they've done it very well, and he has one too. They didn't do it very, very well. They did it very, very ugly. And I feel crippled without my Dewey Can. I also did Dewey Wire and Wire EEPROM, and that's because we don't even have an EEPROM in the Dewey. And so we have to use one of the pins to talk to an EEPROM chip and be able to program that. And he did libraries for that. Again, extending the basic language to add a function to be able to do EEPROM. And so I've included that. I told you we took away the one of the USB ports. We don't have it at all. And it's normally defined as serial in the language. And serial USB is the native port that goes directly in some pins to the microprocessor, and that's the one we do provide. And a defined statement simply says that what you know to be true is no longer, and hereforth something else is truer than what you had. What you thought was serial is now serial USB. And that means I can just say serial all through the program, and it will redefine that when it compiles to serial USB. And so I can write a program and I leave that in and use it on this one. Or on a regular Arduino Dewey, I can comment that out, which you do by 2 backslashes. See where it says these 2 lines redefine any serial calls? The 2 backslashes mean this is entirely frivolous information the compiler will never see. And so that's define. And then this is kind of hard to explain. A couple things are. It's simply a template that lets me do something very strange with print statements that I love to do, and that's more C++ stream-like, that's not normally done in Arduino. Normally then you define some variables, and of course, as Colin will tell you, all global variables are evil in C++, which is, I suppose, my attraction to them. I love them. If you view a device as a state machine, certain variables represent the state, and anything in the program should be able to change those. And it's not to communicate with other sections of code, it's simply to do whatever it does to the state. And I think that way, which leads me to kind of global variables, rather than a master object and layers of them. I would acknowledge that that's recognized as poor coding practice, and of course one of my favorite techniques. The first one that I define here kind of gets to be an advanced topic. It's a class. I'm going to create a new object, but I really don't need to do anything with the object. I don't need to have it do anything. I just want it to be a container for some variables, and you'll see why in a second. I'm going to call this class EPROM variables. It's public, and I have 8-bit variable CAN port, 32-bit variable data rate, 16-bit variable transmit time, and an 8-bit variable vars good, and that's contained in there. And then I'm going to instantiate or create an object using that class called myVars, and it's of the class EPROM variables. Now from there on, myVars is an object containing those variables, and I can access it as myVars.canPort, myVars.dataRate, myVars transmit time, etc. This is CanFrame outFrame. CanFrame is also a class, but it comes out of Collins Dewey Can. And so I'm going to call that outFrame, like I call this myVars, but it's an object of the class CanFrame, which I got as an extension to the language simply because I included Dewey Can in the program to begin with. This is defining variables as a float. My version number, it's called version, it equals 1.00. 16-bit unsigned integer, which is what UINT is. We're going to call it page, and I'm going to set it to a 100. An integer, which in the Dewey is actually a 32-bit number if I don't define it any further. I. Unsigned long, elapsed time, timestamp, start time, and last time. I don't really initialize them. Boolean is a type of variable that can be true or false, or 1 or 0, and we're going to call that debug. And an unsigned integer of 8 bits, log cycle equals 0. So I'm just defining some variables I'm going to use in the program, and actually this is my skeleton for any program. Here's some methods. These are simply functions I can call, and I can put them at the beginning of the program, the end of the program, wherever I want. And one of them is initialize can. What do I need to do using can Dewey to initialize a can bus? And I have 2 normally, but on the EVTV Dewey I only have 1, and 1 is known as can 0. And I'll explain this. Pin mode 48 output, we use pin 48 for the hardware transceiver to turn it on. And so I kind of have to do that, define it as an output. And this is a statement, can 1 begin, and that's defined in the library. This is not part of the C++ language. It's not part of anything you have to remember. It's an additional command that I get from reading about can Dewey from Collins library. And to begin, I want to set a data rate in that pin that I'm going to use to select that transceiver. And so the data rate, as we know, might be 500,000, or it might be 250,000, it might be 125,000. Actually, it's almost always going to be 500,000 or 250,000. And we're always going to use pin 48 because that's what we have wired on the board. If that comes back without errors, I'm going to print a line that says it's true. The rest of this is very interesting, and it's the power of can Dewey, and he's going to describe this in more detail later this week. But just really quickly, remember I said I could set masks and filters in the hardware? Well, I can set them right here. I can say can 1 set RX filter 0, 100, 0x7 FF False. False means it's 11-bit, not extended. 7FF is the maximum address, and that means basically I want all the characters of the address to match. And here's the address I want, and that's 100. And then I have can1 set call, and this is the filter number, 0. Can1 set callback, 0, colon, comma, handled can frame. These are a pair. I set a filter if I receive that message, and only that message, 100. I can route that message to another, some of you might call it a subroutine, we usually call it a function or a method in C++, but a code segment that handles a can frame. As you can see, I have message 618, and I want all bits to match. Go to the same one, 274, 1D6, 308, and in fact, they're all going to handle can frame. This is a skeleton program. I can do a different function for each message. I just happen to have them all set to the same one here. But as these messages come in, this is a list of them I want to pay attention to. And if they come in, depending on their message ID, I'm going to do something different with it. And he's got this all worked out where I can just make a list and then write the routines for each one of them. And this initialize can is itself a routine. And here's the can 0 version, and it just says can 0 set general callback to handle can frame. So I don't have to mask on individual IDs. I can send them all to one. This is a can Dewey thing, or a Dewey can thing. What I like about it is I don't do any processing. If I don't get a can message, I don't do anything. When I receive one, it generates an interrupt, stops the program wherever it is, and sends processing to the function that I just entered there. And that function normally doesn't do anything at all, and you never call it. It only happens if a message comes in with that message ID. So I'm not polling anything, I'm not looking for canned messages. I don't care if I ever get a canned message in the rest of my life. I don't care. But if I do, I have a plan of attack. I've got a routine designed just for that message. And it'll never be called unless I get the message. And until I get the message, I don't care. And he's got all that set up, and this is how you call it. Ooh, that's fun.
Sorry, John.
Okay. The basics. So I had some functions, and I had some variables, and I had some includes. The basic part of an Arduino program is you have a setup and you have a loop. And when you apply power to the device, it goes through the setup once. And then it goes to the loop. And the loop segment, it starts at the top, executes to the bottom, and goes back to the top forever. And it just runs that. So we get to run through setup once, and then we go into the loop. And in setup, I'm going to say serial.begin 115,200. What's that going to do? Well, we define serial as serial USB. It's going to take my USB port and initialize it at 115K. And that's so I can plug in a laptop and look at it. And I can send it text, and it can send me text. Load validate EEPROM variables. We have to use the wire library he gave us and say wire to begin. I set WPP EEPROM is again a command that I get from wire. And so I can say EEPROM set WPPN, I have no idea what that does, to pin 19, which is just hardwired to their EEPROM. I'm going to use our EEPROM. And I say EEPROM read page my vars. Remember, I set up a structure that had a bunch of variables in it, with myvars.can open and myvars.data rate, all that. I just read all of that in a block. And the reason we do this is the EEPROM kind of has a problem. It's slow. And so can require a lot of speed at times. And so I only want to read and write the EEPROM as little as I can. I'm not going to read and write each variable to it. I'm going to make a block, and every once in a while I'm going to write to it when I'm not doing anything else. And certainly not anything important, because it's going to take a while to come back. But it's a lot shorter time if I do it as a block than if I do individual variables. And so I EEPROM read page my vars, that's going to go to page, which we defined as page 100, and it's going to read my vars into memory. And then it's going to go to memories and say if my vars.vars good, vars good was one of my variables, not equal to 20, initialize EEPROM page. Why did we do that? When I do initialize the EEPROM page, I set my vars to 20. And if I wrote it to EEPROM, 20 will be loaded there. Next time I load the thing, when I check it, it'll say 20. If it doesn't say 20, I never had anything in EEPROM. And so it's a little bit circular, but I don't have to initialize it except the first time. And after that, it's always going to read 20. I always have something in EEPROM to read into that. But when you run it the first time, you don't have anything in EEPROM. So all those variables will be empty or 0. If exclamation equals is not equals, I'm going to go initialize it. And basically, I set some values and write it to the EEPROM first time.
How large is the page?
How large is a page? 256 bytes.
And do you pad out your myvars struct to occupy 256 bytes?
You don't have to. But you are kind of limited to 256 bytes.
Sure, but where do the rest of them go? If myvars is only 10 bytes and you're reading a whole page, that read routine doesn't know to stop at the size of myvars, so it's just going to keep going, right? Stomping on memory, just hammering whatever happens to be on the EEPROM over all your global variables.
When we write it, we write a block.
The function read is a template in C++, so it custom generates a read function for the size of myvars.
Oh, it is reading size of.
So
okay.
It's a template, so it's an automatically generated function in C++, specifically for that structure.
Yeah.
That's why it only reads the certain amount. Write, you haven't seen yet, but EEPROM.write is the same thing. It's a template that only writes that many bytes.
I knew there was a reason I hated templates.
Now I thought we were writing a whole block at a time.
Well, the EEPROM always does, but you're only sending a specific number of bytes.
So when we read, we're reading a block. His question is, what happens to the remainder?
It just quits reading.
Yeah.
Okay.
Brings up the question, what if I put more than 256 bytes in the myvar structure?
Catches fire.
That routine will fail.
It will fail. But when it fails, what happens?
EEPROM blows up.
It probably just writes the first 256.
Yeah.
Yeah, I probably would.
So
You could have it generate a compile time error.
That's a very simple
you
library.
can put in a check, but the amount of data you usually have to have from program to program is pretty trivial.
Sure, but I wouldn't underestimate the stupidity of the programmers trying to use that routine.
But I never do. Yeah. I'm gonna say that all went good. I guess we can go look at initialize.
I'll turn that down for you, Jack.
Here's initialize EEPROM. I'm gonna make up some shit, put it in the structure and write it to the EEPROM. If I didn't get a 20 back, it must be the first time. Here's what I'm gonna do. CAN port 0, data rate's 500,000, transmit times 550, my var's good as 20, and I write it. That's the initialization, it's just the defaults. If you haven't run it yet or you haven't changed it, that's the default values that I'm using. So we're in the setup. I'm going to print on the screen so I know, hey, you got through setup. It's all good, baby. Everything worked. Last time, start time, timestamp, millis equals millis. We're going to do some things with how long has it been since. And I'm going to start out with right now during setup. And millis is a built-in function in Arduino that gives me a count of how many milliseconds it's been since the power came up. And I want to take 4 variables, is it? 3 variables and set them all to that value. And so that establishes right now as our baseline. It's been 2,700 millis since we powered up, and now we are ready to begin, and that's forever 2,700. If my var's got CAN port equals 0, initialize CAN 0. If my var's got CAN 1, initialize CAN 1. If we go back to my initialize CAN, it says if which 0 or 1. So whichever one it was, that's what I'll do. And we're done with setup. And by the way, if this seems tedious, we're very nearly done. I guess. Main loop, 84 megahertz. Shit happens pretty quick. You get a lot done. I don't want to do stuff that often. And so I want to be able to control when something happens. And so I'm going to say, if millis, the number of milliseconds since power up right now, minus last time, which is the last time when I set it to millis, is greater than my var's dot transmit time. I'm going to use transmit time to define how often I want to transmit a CAN message. Then I'm going to do this from here to here. And by the way, if it isn't that time, I fall through to this close brace, which matches the one that opens. So every time I hit loop, if it hasn't been that long, I don't do anything, I just loop again. Now this is a skeleton. You can put stuff in here or in here between these two that happens every time it passes through. Things you want to have done all the time. But the printing the status on the screen or sending a CAN frame, I want to be able to define that time by changing my var's dot transmit time. And I can set that to anything I want. Say 500 milliseconds. If I put my var's dot transmit time is 500, then at the point where millis minus last time is greater than 500, I fall in and do all this stuff. And if we're not there yet, I don't. But if you want to do something every time in the loop, you just put it outside of that. This is not a required structure of Arduino. This is a Jack Rickard way he does it in every program he writes. Because I'm not a control freak. I like myself as a control enthusiast. I want to be able to say what time, how often I do this, and by time, by millisecond. It's not a guess. It's every 433 milliseconds. That's when I want to do it. So I just pencil this in because I know I'm going to want to do some of that. I can do a lot of things in loop. Everything I do in the program goes in loop. You don't see it here because I haven't put anything. It's a skeleton. But there's some things I want to do on my time because I'm a control enthusiast, not a control freak. And so that's where it goes. Again, this is a template I use because I write kind of all these things, not all Arduino programs, all CAN Arduino programs for these boards we make this way. And so that's our loop. Print status. I said I wanted to print status. I actually am a control enthusiast, and milliseconds actually isn't good enough. So I actually have some code here that I always use, and you're welcome to steal, that will give me the time since we started in hours, minutes, seconds, and milliseconds. But I don't use millis, I use micros. Anybody know what a micro is? It's 3 orders of magnitude more powerful than a milli. It's a microsecond, not a millisecond. And so, it's simply some math to generate the number of hours, minutes, seconds, and milliseconds since power up. And that's all that is. I'm going to set up a buffer, just a container for characters that I'm going to print to the screen. And I'm going to define with a function called sprintf, standard C++, standard C actually, sprintf. I'm going to use that buffer. And here's some text I'm going to put there. And here's a variable that sprintf has a lot of variable definitions, formatting instructions, and you kind of have to look it up. But this is a one of them. And here's actual. I'm going to use the same one. This is an integer, and so forth. And then at the termination of that is the variables I want to plug into these formats in the string. And this has all been commented out, but I want to remember how to do it. What I'm going to do in my skeleton right now is simply have a 2-digit number for hours, a colon, a 2-digit number for minutes, a colon, a 2-digit number for seconds, a period, and a 3-digit number for milliseconds and 2 carriage returns. That's what I'm going to put in buffer, and then serial, and to left a stream function to send the buffer and a carriage return to the screen. And this is not part of Arduino. It was that template, which you're free to steal, in the front that lets me make it look more like real C++, because they do a lot of streaming. And once you get used to it, you don't like the print line and that sort of thing. I wanted to stream it. But you could say serial dot print buffer, and that would be a more Arduino correct way to do that. Serial event run. Hard to explain. We have some standard interrupts in Arduino, and if a character comes in the USB port, it causes a interrupt that we can capture using the standard serial event run void. And so a character, at least one, has come in the USB port, and we, regardless of what's going on in a loop or anywhere else in the program, we're going to stop and go perform whatever's between these two brackets. And you don't want it to be very much. In this case, if serial not available, I'm going to check for input. And here is a whole function for check for input. I'm not going to spend a lot of time describing this. It gets a character from the USB port, and I'm going to do a series of comparisons using the switch statement and do different things depending on what character came in. If it's a question mark or an H, I'm going to print the menu. If it's a uppercase or lowercase d, I toggle debug, which determines how much we're going to show. Lowercase or uppercase I want to set my interval, which is my transmit time. So I can set how fast I send CAN messages. C is to change the serial port. K is to change the serial rate. Again, these relate to variables in my bars, my configuration variable in my bars that I put in EVCON. This is a routine to print the menu. That's all it does. Get interval, if I did do I, then I look for some more characters, convert them with the parse to a floating point number, and store them in mybars.transmit time. Same with get rate. Get more characters and set my data rate. Get port. Get more characters and set my data port. Here's an interesting part. Send CAN frame. In dealing with CAN, two basic functions we do in a CAN program. We send a frame and we receive a frame. Should have had a graphic or something of your structure out of the library, but I'm going to let you describe all that later. You remember how I have my vars and a series of variables? Well, my frame has a series of similar variables, and they're kind of defined. You can access them in different ways. We set that up way up in the beginning. CAN frame, out frame. So we set up that instance of it, and so we can access all those variables. And we can kind of do them, I call it syntactic sugar. I love this, the dot notation. Outframe.id equals 0x700. 0x is telling the compiler this is a hexadecimal number and not a decimal number. I've defined the message ID as being 700. Outframe.length equals 8. How many bytes can you have in a CAN message? 8. But you can also have 1, or 2, or 5. You can't have more than 8. Outframe extended equals 0. We talked about extended and standard addresses. Standard addresses are 11-bit addresses. Extended addresses are 29-bit, and this particular bit you set here, again, this goes to that control area in the CAN message frame.
Why does it go from 0 to 11 and then from 1 to 29? Would it not from 0 to 29? You're saying 0 means
Equals.
1 means something. Oh.
That's an equal sign.
Oh, it's an equal sign.
If I
Yeah.
set it to 0, that means 11-bit. If I set it to 1, it equals 29-bit.
Okay.
If I set them both to 0,
Oh, yeah, okay. I thought
then how would I tell which one it was?
Yeah, I get it.
It's maybe some spaces in there would make that more clear.
Wow.
But I've got it set to 0, that means 11 bit. If I change this to 1, that's telling Collins library we're using extended frames, or 29 bit. This is this RTR that nobody on the planet has ever been caught using. But maybe some people, Colin might be able to talk to that later. I've never found a use for it. And then we have 0 through 7 data bytes. And that is our 8 byte payload. And I'm loading them up. And I'm going to set 0 to 0 and 1 to 0. And then 2 and 3, I'm going to take my transmit time and put the high byte in 2 and the low byte in 3. Transmit time is a 16-bit integer. And I'm going to define that it's an MSB, LSB situation in CAN. That's the Intel protocol. The Motorola protocol would be LSB, MSB. But I'm going to define this one, and I'm free to do this. This is the guy who's writing the damn program. The most significant bit of the 16 bits will go in byte 2, and the least significant bits will go in byte 3. Byte 4 I'm going to define as 0, and I'm going to do the same thing with transmit time again here, and then 0 and 7. Now, why would I be doing all that? It's utter nonsense. It's the skeleton program. I'm just showing you how to load up 8 bytes. You can define them as variables in your program, but you have to keep in mind that each one are 8 bits, and you have to kind of jostle it around to get it in there. And that's not entirely true, but it's true for me. As Colin will describe in a more detailed session later on DeweyCAN, he has different ways of doing this besides data bytes. You can also do 16-bit, 4 of them, 32-bit, 2 of them, or a 64-bit block using different terminology. But I just sort of template this, and I know I'm always going to have to fill in 8 bytes. If debug, remember debug, it was just a byte that I can set, and I can toggle with the key in D, and it sets up a buffer and prints all this data I just did into the buffer, and then sends it out the port to display on the screen. And then it also sends it out the CAN port. So CAN 1 send frame, or if CAN port 0, I'm going to say CAN 0 send frame out frame and mail it. And that will send that frame out on the CAN bus. And you're done. It's gone. As far as you're concerned, it's been mailed. The debug block, I set up a time thing and put all the data from my frame onto a string that'll print out on the screen so I can see what was in the CAN frame. Toggle D, that shows up every time I send a frame. Hit D again, it doesn't. Nothing shows up. So I only want to see that when I am in a debug situation, and then I want to see exactly what the data is in the frame, what the message ID was, the whole thing. If I don't want to see that, this will run faster. I can just send the CAN frame and mail it. And that's a frame sent. Let's handle a CAN frame. And we're going to do that. Again, CAN frame is an object defined in Collins library. But this asterisk frame, we'll always get this mixed up. Is that the address dereference, or?
Yeah, it means that CAN frame's a pointer.
It's a pointer to a memory location containing the received frame, right? I'm going to set some variables for in here. You can see I've cut all this out because I'm doing generics. these were from a routine that actually did something. And so I established some local variables and some global variables. And most of them are commented out. But this is a template for a function to handle an incoming frame. And so I could say aux equals frame data bytes 4, but I'm going to divide that by 10. CHV, charge voltage, equals word, frame data byte 0, frame data byte 1. So I'm going to take 0, 1 and treat it as a word, and so that would be LSB, MSB. CH voltage, well, that's referencing a previous variable. CHA is that frame pointer data byte 3. And so it goes, and that's all I wanted out of that frame. The rest of these are calculations to do cumulative kilowatt hours or something based on the current that came in the frame. Again, this is a template. Again, if debug, I'm going to set a timestamp and print it. And by the way, we're finished. That's an Arduino program skeleton you can actually use to make a CAN frame and send it, and receive a CAN frame and process it. Save your configuration variables to EEPROM. Set a timer to how often you want to do something in your main loop. Use the EEPROM and CANDUI libraries. And so that's a skeleton. That's the start of a program for me using the EVTV CAN microcontroller or the CANDUI shield. And those pin number and assignments will work with that hardware. And I can generate CAN messages and send them. I can receive CAN messages and assign them to take data out of them and assign them to variables. I can print stuff to the screen. I can get commands in from the screen, the terminal program, and I can save my configuration to EEPROM. That kind of covers almost everything I do with CAN. What else? And that's it. And so in that template, I've got almost everything I need to do a program. After that, it's dealing with specific data, specific messages, and so forth. Data.
Yeah, the question is, what happens if you're processing and another message comes in that you're interested in?
Very good. Whole program suspension stops. We go process that inbound frame, and we resume where we left off.
Okay, so you stack them up.
I have two basic interrupts here. One is a serial event, and one is a receive message. We don't have an interrupt for send message. We have one for receive message. And which is the priority? The CAN message coming in or the serial event?
The serial event.
The serial event would be priority. So we're going to be going through the loop over and over and over again. A CAN message comes in. We go start to process that. A serial event comes in. It stops that. We go process that. When we're done, we go back to the CAN message processing, finish processing that, and then we're back in the loop.
In regard to Al's question, is there a small buffer in the CAN transceiver or receiver as well?
A buffer?
Yeah.
Not my problem, man. That's in the CAN library.
Oh, it's in the CAN library. Is it just in the library or part of it?
Both.
Part of it's in the hardware and part of it's in the
There are
library.
quite a few buffers in there that are invisible.
Right.
And this is my point. I don't have to deal with any of that at all. That's in Collins CAN library and in the transceiver hardware. And whether it's CRC'd outright, went into arbitration, lightning strikes, not my job, man. You're gonna pass my pay grade. If a message comes in and it throws an interrupt, I have a routine to handle. And if a message never comes in for the rest of my life, we just won't be doing a lot of CAN programming after that because it's kind of useless. And so I'm trying to limit my responsibility and need to know on CAN to some degree. We'll be happy to discuss the details for the ever curious, but my sense is that a lot of people are put off by CAN not because they know too little about it, but they know too much. And it's repeated over and over and over again, totally useless information. How many CRC bits are in a CAN traffic message?
Who cares?
Who gives a shit? It's done in hardware. I'm never, it's not that I don't care now, I'm never going to care. You can't make me care. And so, let's cut through all the stuff. It's about message IDs and data payload. That's what it really is. A little goofy stuff about standard and extended. Sorry, you got to deal with that. And Colin retains some of that, or passes on to you some of that masking, filtering power with that 7FF. See, there's some, and he may be persuaded to cover that in more depth, but it's actually a bit map against your message IDs, where you can say I want all 618 messages, or I want all 61 whatever messages, 610 through 61F, or I want all 600 messages, or I want all messages. You can mask that different ways for different digits of it. Actually, it's very powerful ways, but until you get to that need to do that, it's in the example in the library. Libraries, you download them. Your Arduino installation has a directory called libraries. It has that in Windows, has that in Mac, has that in Linux. Take the library and put it in the libraries. You're done. That's what you do with libraries. It's not that hard.
Would you like a bug report?
A bug report.
Yeah, I can see a bug up there. Do you want to know about it, or do you not care?
It's
Pretty innocuous. It's only in the logging. It doesn't really matter.
it's on the what?
In the logging, the millisecond count doesn't have enough leading zeros.
Millisecond count. Yeah, that's got 3.
Yeah, but you're calculating it with 4 digits. Milliseconds is a misnomer. It's 4 digits of fractional seconds that you're printing out.
You know, it might be.
Yeah.
I might be print 4 digits.
That'll be number 0 from 99.
But I probably don't care about the last one.
Oh, but it won't truncate it. It just won't have enough leading zeros if it happens to be less than 10,000.
So wait, is it really tenths of a millisecond instead of milliseconds?
It is tenths of a millisecond.
Yeah, that would make sense.
So if it happens to be 500 tenths of a millisecond, then it's going to print 0.500 as if it was half a second.
I think I'm generating it to 4 digits, but I only want to print 3 of them. That's milliseconds, which is what I'm wanting, but I'm taking it from micros.
Yeah, but you're calculating tenths of a millisecond, and that will print out, %D will print out the number. All the 03 does is determine how many leading zeros.
Mm-hmm.
You know, the question is what's on the end of that line with the S for
You can see it. It's milliseconds.
that? Oh, then it's
Here?
Yeah, that's the one. Yeah. It just ought to be 04 if you want to have it read correctly.
I want to go up to 999 milliseconds, and I don't need 1,000. Then I'm into micros. I just want the first three.
Okay, well then the millisecond calculation
Is it?
is off by an order of magnitude.
If I take micros divided by 100,
There's 1,000 microseconds in a millisecond.
uh-huh.
I thought that was deliberate.
I think it is. I'm trying to remember why I did it that way.
More precision.
I've used that bit of code like 300 times.
You want more digits, so.
No, okay, maybe I do. I think I might. Run the program later and see what it spits out.
Yeah. It'll only bite you, 10% of the time.
Here is one more image. This is the other device. This is a shield you run on any CAN Dewey. It's got ground and 12 volts. Then it has an input for a negative temperature coefficient, which is just a temperature sensor that I ran into an analog input with some resistance where I could easily read a GM temperature sensor, believe it or not.
It's for the coolant heater.
For the coolant. I thought that was too specific, but there's a lot of GM temperature sensors out there, and they all work about the same.
They're all 2.5.
CAN 1 high and low, CAN 0 high and low, ground, software CAN, and load. Load is two terminals where you put a resistor, which Mark will explain to you what it does, because I always put the wrong resistor. That's why it never works for me. Ground, think of that as CAN low. And software CAN is our one-wire CAN. You want to run this at 33.3K. That's what the Tesla supercharger and CHAdeMO conversation operates on. It's also what the Evans Spocker heater operate on, which is where we started with this. Here are termination resistors and caps for CAN 0 and 1, and we replaced solder pads with switches. Here's a micro SD card you can log data to. You'll never use it. It's called CAN Dewey version 2.0 Theodora because Apollo's mother's named Theodora and she's dying. Here's your CAN transceiver chips and your EEPROM chip. And so while the EVTV Dewey has one CAN port and an EEPROM chip, this gives you two CAN ports, a software CAN port, the EEPROM, and so forth. Now understand, you can set these two CAN ports at different speeds, for example, and receive CAN messages in the 250K bus and put them out on the 500K bus, or take messages in the 500K bus, put them out on the 250K bus. You can use this to bridge, and it will work fast. There's nothing that you're not going to outrun this Arduino Dewey in this shield with a car.
That's what we're going to be doing with the heater.
So you can use it as a bridge. You can use it to read two CAN buses at the same time. That would be confusing in the log. But it's very powerful. Best and highest use is with a program called the Generalized Vehicle Reverse Engineering Tool, which Colin wrote, which has none of the nonsense I just showed you in my little skeleton program. It's very nicely done. And then you hook up your USB port, and the other part of the puzzle is a very nice GUI program, Windows type, GUI called SavvyCAN, that has all kinds of analysis and ways to log huge files. I've logged 10 million frames, no problem. At very high data rates, 2,800, 2,900 frames per second in the real world. And we actually use to reverse engineer it well enough that I've got the Tesla drive unit pretty much done. And Colin will be doing sessions on the Dewey CAN library and Geobret and Savvy CAN. And that's why I said you never really use this card. By the time we got that far along, the card's slow and it has a limited size, of course. A laptop usually has a lot of memory and it's fast. So we kind of never really logged any data to the card because it's easier to log it to the laptop, and then you have unlimited storage and you're using that software. And so if you've got Savvy CAN, the SD card doesn't make any sense. But it did at the time.
If we want to do GVRET, or if we want to do bridging, so this is just a shield. Should we opt to just run it on an Arduino Dewey, or is it better to do an EVTV Dewey?
I wouldn't even do it with EVTV Dewey. You're duplicating CAN 0. But if you buy this from EVTV, you get an Arduino Dewey, a cable, a little card for the micro SD, a little cable for the OBD2 on your car.
Is the addressing the same on CAN 0?
Yes. Yes, in all respects. It's 0 and 1 and pin 48 and 50, and it's all done there. I also have a version of this in a nice box with a nice connector for Tesloids that aren't as smart as you. They can just pull that connector into the thing, plug it in, and record traffic. And I suppose that would include me because that's what I use. But we also sell it. Nice box and so forth. So we've got two really quite capable hardware tools and then a bunch of software where we're actually so much out ahead of what you need to do with CAN, and nobody knows about it. It's a secret. There's 7 or 8 of us who used it. And we use it a lot, so it works pretty good. And you're welcome to it, but it's probably going to be a slow burn. I don't imagine it'll be a big profit thing for EVTV anytime soon. Kind of for the same reason that Vector's stuff has to be $5,000. There's not a very limited group of people that know about this, but I'm hopeful that if we can do one good thing with our open house, it's to take you guys and get you up where you're not afraid of CAN, you know where to go, you know where the tools are. If you want to do something CAN, you know it's not magic. You're not, stealing thunder from Thor. It's hardly even electronic. We think of it as Sudoku in the New York Times puzzle. It's not really technology. Is this puzzle working?